It's kind of weird. When we talk about numbers, when you first started doing arithmetic with numbers, we start with addition and subtraction, and then we move on to multiplication. The thing with fractions is multiplication and division are a little bit easier than addition and subtraction. But when we're adding and subtracting fractions, the thing that makes adding and subtracting fractions a little bit more complicated is the fact that we need a common denominator. So if I wanted to take 3/5 and add that to, I don't know, 1/4, getting back to the analogy that I've been using around fractions and just sort of what this means, the numerator tells me how many pieces I have, and the denominator tells me the size of the pieces. So when I look at this, I've got 3 pieces that are a size 1/5 and 1 piece that's a size 1/4. So if I want to combine these together, I need to be thinking about these in terms of their equivalent fractions that are going to have the common denominator. Now, we often use the abbreviation LCD, not liquid crystal display, but lowest common denominator. So when I look at 3/5 and 1/4, I'm taking a look at the 5 and the 4, and I'm thinking about what's the smallest number that both of these factor into. And one route for finding a common denominator is always to just multiply the denominators together. Sometimes it's going to be the lowest common denominator. Sometimes it's just going to be a common denominator. So I want to think about 3/5 as its equivalent fraction by multiplying creatively by 1. And the 1 that I'm going to multiply by is 4/4. On that 1/4 side, the 1 that I'm creatively multiplying by is 5/5. Now I'm just using our multiplication rules for fractions to go straight across on the numerators, straight across on the denominators. So 3/5 is equivalent to 12/20, and 1/4 is equivalent to 5/20. So in terms of my final answer, I'm looking at 17/20. Anytime we're adding or subtracting fractions, we've got to start by finding that common denominator. There's something really magical that happens when I add an equal sign. Now I have 2 sides of an equation. But without that equal sign in there, I don't have an equation and I don't have 2 sides to something. So when we talk about multiplying by the common denominator to eliminate the fractions, that only works if I've got 2 sides to work with. So unless I had something like this, now that I have an equation and I've got fractions, I can totally take this and multiply both sides by 20 to avoid dealing with fractions at all. I can distribute the 20 in, and then I'd have 60 divided by 5, or I can think about the 20 divided by 5 gives me a 4. So 4 times 3 would give me 12. Distributing the 20 in here, 20 divided by 4 would be 5. Fractions are gone. Life is good. I'm looking at 5x is equal to 28, and x is equal to 28/5. Unfortunately, if I don't have that equal sign there, and I'm not talking about an equation that I'm solving for, if I just have an expression, which means I got some mathy stuff but no equal sign, if I need to simplify this, or if I need to add or subtract these things, I have to get a common denominator to move forward. So it's subtle, but that equal sign is powerful. I hope that helped to answer the question. But let's do some more examples.
Yeah, I answered my question. Thank you.
Okay. So if we're just talking about expressions and there's no equal sign, I don't get to use the magic shortcut, unfortunately. Oh, and really the instructions are probably going to be my least favorite algebra instructions per use. You know, something like simplify. Well, if I'm adding or subtracting fractions, then that phrase simplify means that I should try to combine these to a single fraction if I can. Whenever I'm adding or subtracting fractions, I need a common denominator. The other way to think about that is if I had an equal sign, what can I multiply by to get rid of this stuff? That should be what our common denominator is. It is always fine, but not always the most efficient route, but it's always fine to make your common denominator all of the denominators multiplied together. So here, if I think about wanting my common denominator to be x times 3, that means that the 2 over x would need to be multiplied by 1 in the form of 3 over 3, and 1/3 needs to be multiplied by 1 in the form of x over x. After I do this, the 3 times 2 will become a 6, and then 1 times x would leave me with a minus x. I'll be honest, we don't usually write the x times 3. There's something about that actually, just because I'm habituated to it, feels wrong. I'm going to rewrite this as 6 minus x over 3x. There's actually nothing wrong with this. It's just a mathy thing that we tend to put the coefficient in front. And this is the best that I can do. This, weird as it may sound, seems more simplified to a mathematician than where we started. I think the bottom line is we need to be able to recognize that they're equivalent. So I need to be able to start with something like this and break it apart into 2 fractions by visualizing that as 6 over 3x minus x over 3x, and then simplifying each of those. And I need to be able to start with this and go back to here. There are going to be times in calculus where it's helpful for us to have these combined together. And there are going to be times in calculus where it's more helpful for us to be able to split it apart. So what we're working on right now is just thinking about different ways that we can rewrite an expression to find the one that's best for what we're doing in the moment. Starting with this expression, I've got addition, so I know that I need a common denominator. One of the tricks to save yourself time is to be on the lookout for that lowest common denominator. And usually, in order to find the lowest common denominator, I want to make sure that everything that I have is factored as much as possible. So when I look at that 3x plus 6, I can see that 3 and 6 have a 3 in common, and I could rewrite that to say 7 over 3 times x plus 2. By doing that, I can see that between these 2 fractions, a common denominator would be 3 times x plus 2. This piece already has everything I need. This one over here would just need a 3 in the denominator. So I'm going to multiply by 1 in its form, 3 over 3. For those of you that watched the weird number, every time I do this, I think about that 1, concentrating really hard, getting the weird look on its face, and then popping into a 5/5. Well, this time my 1 popped into a 3/3. I know it's dumb. I just like that imagery is stuck in my head. So when I simplify the top here, I'm looking at a 7 plus, and then when I multiply these two together, I'd get 3x. And again, I would leave it right here. If it's in a factored form and the instructions were to simplify, we should generally leave it in a factored form when we're done. My starting point here, I know that I've got either addition or subtraction, in this case, subtraction of 2 rational expressions, which means that my first step has to be to find a common denominator. And before we can do that, we're hoping to get things factored. So I will give you 30 seconds to factor both of those denominators. Hoping that was enough time to get stuff factored. Let's go ahead and slide in here. I've got x plus 3. I'm going to pull a 2 out, and then x plus 4 minus 4 times, and then my x squared minus 16, and call that an x plus 4 times an x minus 4. Well, looking at these two pieces, my common denominator is going to take everything that's in a denominator, but I'm only going to take it once, if that makes sense. So these both already have an x plus 4. I don't need to put 2 of them in my common denominator. This has an x minus 4, so I'm going to need an x minus 4 in there, and this has a 2, so I'm going to need a 2 also. When I find my common denominator, now I'm thinking about how do I creatively multiply by 1, which of its forms do I need to multiply by so that this denominator matches this. Since the x minus 4 piece is what's missing, I'm going to multiply by x minus 4 over x minus 4. On this side, I'm missing the 2, which means I'm going to multiply by 2 over 2. When we write this down here, we're going to end up with, from multiplying this out, some kind of quadratic minus 8. Because we're getting a term that isn't just a number on the top or isn't a linear term, there's a chance that what we end up with will have a factor that will simplify with something on the denominator. So we're going to want to multiply this out, not leave it in 2 pieces. So let's get to distributing. X minus 4 times x plus 3, and take that x, distribute it in to the x and the 3. X times x would give me x squared. X times 3 would give me a plus 3x. And then I'm going to have that negative 4x times x and negative 4x times 3. So minus a 4x, negative 4 times negative 3 would be negative 12. And that's all just from the first fraction. And on my second fraction, I've also got a minus 4 times 2. or minus 8. Well, if we simplify the top, I think I'm looking at x squared minus x minus 20. As a last check, because the instructions were to simplify, now I'm thinking back to the stuff we've been doing for the last couple days and saying, well, if the top factors and they have a common factor, then we should cancel those out to leave a 1. Okay, looks like most of you have it here. X minus 5 times x plus 4. Which means that my x plus 4 over x plus 4 can cancel, leaving me with a 1. Now I kind of ran out of space. I don't want to write all the way down at the bottom of the board, but final answer now, totally simplified form. I'm looking at x minus 5 divided by 2 times x minus 4. This is actually more how division problems tend to show up in calculus. And one of the things that happens, or one of the things I'm going to recommend, is write big, use as much paper as you need. If the lines on the page are throwing you off, use the back of some random printout you have laying around, so that you've got a clean sheet of paper. Because when I look at something like this, it's easy for that middle division bar to kind of get muddled when we're looking at this. But this is saying that I've got this one fraction on the top and it's being divided by this other fraction. So we're going to use that rule or that tool that says when I'm dividing by a fraction, that's the same as multiplying by the reciprocal. Now this has taken us back to stuff from last week. Visually, when I look at this, because it's all multiplication, I know that I can group things together. Like I can group the numbers together. Thank you. My 5 became a 2. Appreciate that. Thank you for the heads up. So I'm going to deal with my numbers. So 3 divided by 6, that's going to leave me, I can think about that 6 as 3 times 2. So my 3's will leave me with a 1 and a 2 on the bottom. Then I can move on to think about my x's. So I'm looking at x to the 5 minus 2. And then my y's, using that law of exponents, y to the 7 minus 4. Well, if I clean that up, there are a couple of different ways that we can express this. I'm going to end up with x to the 3rd, and I'm going to end up with y to the 3rd. And I've got a 2, but this is equivalent to writing 1/2 x cubed y cubed. Again, this is one of those things where sometimes this is going to be the better form for it, and sometimes this is going to be the better form for it. With the vague instructions of simplify, either of these are correct answers. I just want to step back and say, again, this phrase simplify, it's a little vague, but we have a compound fraction because I've got like fractions over more fractions. I've got subtraction going on. I've got addition and subtraction going on down here in the denominator. So there's a lot going on in this problem. And that phrase simplify, we're hoping to get this down to a single polynomial divided by a single polynomial. Factoring stuff if we can, canceling things out if we can. There are a couple of different approaches that we can take to this. One option is to step back, look at the entire thing and say, because I've got fractions on the top and fractions on the bottom, is there a single common denominator that would work for all of it? And the single common denominator that I'm seeing that would work for all of it is x squared. So one option is, rather than individually getting common denominators for each term, one option is to multiply the entire giant fraction by 1. That same idea that I'm creatively multiplying by 1, and my creative multiplication by 1 here would be x squared divided by x squared. This is not our only option. But if we go this route, then I'm going to take that x squared and on top, distribute it into the 1 and also distribute it into the negative 9 over x squared. Well, when I do that on the top, I'm going to end up with x squared. And when I distribute the x squared in here, those x squareds are going to cancel out, leaving me with just x squared minus 9 in the numerator. When we do the same thing in the denominator, and I take that x squared and distribute it in, I'll distribute it into the 1 and get x squared. Distribute it into the negative. You know what? It's distracting that I'm pointing this to the bottom, and I apologize for that. I was just trying to be efficient with my arrows, but it would be more accurate for this to look like I'm distributing it here. So x squared times 1 would give me x squared. On this next term, I'm going to have x squared times 5 divided by x. And I'm just going to write that out. So I'd have 5x squared over x. And when I distribute here, I'd end up with 6x squared divided by x squared. Well, both of these can now simplify because x squared over x squared is going to be a 1. And that x squared over x, I can break that x squared apart, think about it as x times x, and one of those is going to cancel. So on top, I've got x squared minus 9, and the denominator, I'd have x squared minus 5x plus 6. Now I'm ready to factor the top and the bottom and see if we have anything that cancels out. So I'll give you a second to, okay, not 1 second. I'll give you like 40 seconds to factor the top and the bottom and see if you can get anything to cancel. That top x squared minus 9, that difference of squares shows up a lot That's one that we want to get really fast with factoring. So x squared minus 9 is going to become x minus 3 times x plus 3. And this one I've been using a lot too. The numbers are pretty nice and friendly. I know that in terms of 6, I've got 2 factors, 6 and 1 or 2 and 3. But I need them to have the same sign because this is a positive, and I need the difference between, I need them to be the same sign, and I need them to both be negative. So -3 and -2 is what's going to work. And then we can see that that x minus 3 over x minus 3 would leave us with a 1. And my final answer would be x plus 3 over x minus 2. Way up here at the top, I said that this was just one option we have to work through the problem. I happen to think that this is the faster option anytime that we've got these compound fractions, meaning I've got fractions divided by fractions. It's often the fastest route to find an overall common denominator to multiply everything on the top by and everything on the bottom by. But we could also do this, option 2, in 2 steps. I'm going to erase stuff unless there were questions, but we're going to get down to the same answer in a second. Oops, yeah, that's right. Option 2. We already know what the common denominator on the top and bottom both were. We know that it was x squared. So the other option is to just separately combine the terms on the top with a common denominator and combine the terms on the bottom with that common denominator. That means that on the top, I'm going to need to change that 1 into the x squared over x squared form. And then on the top of this giant fraction, that means that I'd have a single fraction with x squared as the denominator. And in the numerator, I'd have x squared minus 9. Doing the same thing to my denominator here. 1, we're going to need to again turn into that x squared over x squared form. 5 over x, if I'm going to give this a common denominator of x squared, and then I need to squeeze in x over x. Rewriting out the entire denominator, we've got that common denominator of x squared. And for my numerators, I've got x squared minus 5x plus 6. If we went this route, then we've got one extra step, which is now that I have a single fraction divided by another single fraction, we can change that division to flip it and multiply so that I end up with x squared minus 9 over x squared times x squared over x squared minus 5x plus 6. And now the x squared over x squared cancels out. And we're back to the same place that we were a second ago, factoring the numerator and factoring that denominator. Two options. They're both going to lead us to the same place. There is no right answer. Oh, sorry, there is a right answer. There's no right choice in terms of option 1 or option 2. It comes down to what feels more natural to you, what feels like a process that you think that you can consistently follow. I will also say for me personally, I might make a different choice in a different problem. For example, if it's hard to see what the overall common denominator would be, then I'd probably just separately get a denominator on the top and a denominator on the bottom. This happened to be a problem where it was easy for me to look at the whole thing and say x squared is a common denominator for every fraction up there. I can't really think of a time in calculus that that problem is going to show up. So I'm going to let you in on a little secret. The problem that is going to show up in calculus is us doing that problem in reverse. Here's what I mean by that. There are going to be times where I need to take something that looks like this and turn it into a compound fraction. There are going to be times where I'm going to have to look at this and say, I need to either factor an x squared out from everything, even though it doesn't really factor out, or I'm going to need to divide every term by x squared and show how that simplifies. So it's more likely in calculus that I'm going to start with something like this, have to find what's the largest power of x anywhere in this problem, identify that it's x squared, and then divide every single term by x squared. So if I go through this and I divide every term by x squared, I need to be able to then look at this and turn it into that original compound fraction that we had. I know it feels weird that we're practicing going from here to there, when in calculus, we're more likely to have to go from here to here. But one of the points that I'm trying to make is that being fluid with your algebra, being able to go kind of back and forth between different equivalent forms of an expression is super helpful all throughout calculus.